This is another thin film problem. Let's draw the picture first so we can see what's happening. So here is our thin film, and they tell us that it's essentially water surrounded by air. So we have air up here, and of course the n is going to be 1. And on this side, it'll also be 1 since it's surrounded. And then the thin film, in this case, they tell us that it's basically surrounded by water. Now, at first I was thinking that maybe the index of refraction would be different since it's soap in the water with it, but they don't give us any other information on what that index of refraction would be. So we'll assume that it's 1.33 for water. If we draw the light as it passes through here, let's see how the phases would change. We'll get some reflection, and then it will come in here, and we're going from low to high. So we'll get one phase change here. Now we're going from high to low, so we won't get any phase change with this one. We'll get some reflection here and like that. And so we have one phase change, and we want to know what wavelengths are strongly reflected. So that will be constructive interference. And so the equation for one phase change for constructive interference is 2t is equal to m plus 1/2 lambda over n. Now we want to solve this for lambda, so we could multiply both sides of the equation by n, and that will give us 2tn is equal to m plus 1/2 times lambda. And now we'll just divide both sides of the equation by m plus 1/2. So we have lambda is equal to 2tn divided by m plus 1/2. So now we have our equation, and we have pretty much all the information here. The only really other thing that they give us is the thickness. So T over here will be 390 nanometers. And let's see, we want to figure out what visible wavelengths are strongly reflected from this. And so since they say visible wavelengths, what we'll basically have to do is just start with m as 0 and work our way up until we're outside of visible wavelengths. So m for 0, if we start there, we'll have lambda is going to be equal to 2 times the thickness, 390 times 10 to the negative 9 meters, times n, which we said is 1.33 for the thin film. And all that will be divided by m plus 1/2, so 0 plus 1/2. We'll do the same thing for m is equal to 1. So we'll have 2. All of this will stay the same, of course. The only thing that's going to be different is the m. So now we have 1 plus 1/2. And then we'll do m equals 2. And let's also do m equals 3. And we'll see where that gets us. We can plug these all into the calculator pretty quickly since it's all of the same thing. We're just changing one number. All right, so now I wrote out all of our equations. Let's start off with those 4 and see where that takes us. So we have 2 times the thickness, which we said is 390 times 10 to the negative 9 meters. And then that gets multiplied by the index of refraction as well, so 1.33. And then all that's divided by m plus 1/2. So for the first one, we get 0.5. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2075. So when we look at a graph of the electromagnetic spectrum, 2075, that puts us into X-ray range. So of course, that's not going to be visible light. So now if we go back and let's do 1, so we'll copy this forward, and then the only thing that we're going to change is we're going to divide it by 1.5 now for m equals 1. So that gives us 692. So 692, we can round that to 690. What color is that going to be? That is, of course, in the visible spectrum, which of course is 400 to 700, and that's going to be a red. Now let's go to m is equal to 2, and we have 415, and 415, 415, you could round that if you wanted, of course, to 410. I'm going to leave it at 415. 415, and that is going to be a violet kind of purple color. So we'll just say violet. And then let's go to n+3. That's likely going to put us outside of the range, but let's just check. So we have 3.5. And so yeah, 296, that's out of the range. So 296 nanometers. And so we're well beyond visible light spectrum there. Okay, so the colors that it's going to strongly reflect is red and violet, which will give us kind of a purple color. So these are the two visible wavelengths that will get strongly reflected in this situation, and the colors for them are red and violet.